Okay, good morning. Getting right back into it. It's always a little weird to come back after vacation and then try to work again. I mean for you guys, not me. No, I'm just kidding. Okay, so we have to get right back into it. Homework is due today, so hopefully you enjoyed doing that homework, as well as if you did the extra credit assignment, the energy selfie, you can either email it to me or have it printed and turned in now. I won't be accepting any more of those after today just because we need to be done with it. Because we have an exam next Tuesday, so a week from today. So the bad news is we have an exam. The good news is this is the easy exam of the entire semester. Okay, I don't tell you that so that you'll not study and just blow it off, because it can be a very difficult exam if you don't know the subject material. But I think by and large these types of problems are simpler, a little bit easier to understand than some of what we did previously in Chapter 5. So Chapter 6 is all about refrigerators, heat pumps, the Carnot cycle, and then we'll have a little bit about entropy on the exam. So if you want to go ahead and start looking at some of those lecture notes or the sections that we're going to cover on Thursday, give yourself a little bit of a head start. Do the reading in advance so that it makes sense to you when we start talking about it on Thursday. So if you look at the course outline, it will tell you which sections we'll be talking about on Thursday, and those will be covered on the exam as well. So get a head start on that. So today we're talking more about the Carnot cycle and Carnot heat engines. And if you remember from before, the Carnot cycle is an idealized cycle which allows us to analyze a system using the best case scenario. So it gives us the limits upon which we can compare all other systems. So if we're looking at the Carnot cycle as the idealized cycle for a heat pump or a refrigerator or a heat engine, then when we have a real device and we compare it to that cycle, we can say, oh man, I'm only getting 50% efficiency, but the Carnot cycle, the maximum efficiency is maybe 55%. So really it's not as bad as we think. Sometimes seeing really low efficiencies make us worried, but in reality when we're converting heat to energy or to work, we don't get very high efficiencies anyway. Okay, so just by way of review, comparing the three different types of systems that we've talked about in this section, we have a heat engine which has thermal efficiency, and it is work net out over Q sub H, so again the desired outcome over the required input. Whereas heat pumps and refrigerators use something called a coefficient of performance, which is different from efficiency. It's always greater than 1 or should always be greater than 1. And our desired output then is either removing removing heat from a refrigerated space to make it colder, or adding heat to a warm space to make it warmer. So depending on if it's operating as a refrigerator or a heat pump, our desired outcome is different. However, the required input is always work. It's always the same. So our coefficient of performance for a heat pump or for a refrigerator can be denoted in terms of heat and work, or just using the heat terms. Because of the first law energy balance, we know that work is equal to QH minus QL for those systems. So remembering these equations and differentiating them is less important than remembering the fundamental principle of desired outcome over required input. So the quiz that we had last lecture kind of tested whether or not you understood that concept, and there were some who struggled with that. So rather than trying to memorize equations, memorize fundamental principles. Of course on the exam these will be on the equation sheet, but isn't it easier and better if you understand the underlying concepts? The Carnot cycle we introduced last time, and this is a cycle which consists of 4 reversible states or reversible processes. So we have states 1 through 4, which are denoted on a PV diagram. And if we remember from discussions in Chapter 4 and 5, the area enclosed on a PV diagram represents the network out or the network in, depending on the direction of our processes, whether we're undergoing compression or expansion. So the Carnot cycle, and plotting it on a PV diagram shows us several different things. One, we can look at those processes and know and understand kind of what's going on in the system. So if it's following along a line of constant temperature, then we can know that. We can see if the volume is increasing or decreasing, we can see where heat is added or heat removed, and then again, we can look at the total network output or network input for the system. We also talked about some principles of the Carnot cycle, which are in essence a restatement of Kelvin-Planck, but in a slightly different way. But they're all expressions of the second law of thermodynamics, so that the efficiency of an irreversible heat engine is always going to be less than the efficiency of a reversible heat engine, meaning that when you have irreversibilities within your system, it will decrease your efficiency. And if we have the same two temperature reservoirs, the reversible heat engine will always have the greatest efficiency. That's the max possible case. And then if we look at efficiencies of all reversible heat engines, so if they have different working fluids, different compressors, different condensers or evaporators, so long as those thermal reservoirs are the same, the efficiencies of those systems, the max theoretical efficiencies of those systems will always be the same. So that's based on the Carnot principle number 2. And that's useful to us because despite whatever processes we're undergoing in our heat engine, we can always figure out what the max theoretical efficiency would be. And we can use this in a couple of ways. One, it's to see whether or not our system is performing as well as it could be, by comparing it to the theoretical max. The other kind of nice bit is that we can look at the efficiency we're calculating for some designed system, and if it's somehow greater than this Carnot efficiency, then we've done something wrong. Okay, so there's something incorrect in our calculations, and we're actually designing a system that isn't possible to exist in real life. We need to use the thermodynamic temperature scale whenever we're calculating Carnot efficiencies, and again, it's because this temperature scale is not based on any individual working fluid. The Fahrenheit scale and the Celsius scale are based on freezing and boiling temperatures of working fluids, whereas the thermodynamic temperature scale is based on absolute zero. So when we're calculating efficiencies and using temperature in our equations that don't involve a change in temperature or a delta T, we have to use the thermodynamic temperature scale. So it normalizes it. We don't have to worry about whether it's water or refrigerant. It's valid for all materials and properties. So Carnot heat engine operates using the regular Carnot cycle, and it's reversible. So each process along that cyclical path itself is reversible, which makes the entire process or the entire cycle reversible too. So 1 to 2, 2 to 3, 3 to 4, 4 to 1, each individual process is reversible, so the whole thing is reversible. And this is a theoretical process. Okay, the Carnot heat engine is one that we use as a model. It's not necessarily one that we can create in real life, but again, it offers the bounds on the max possible efficiency we can expect to achieve using a real heat engine operating between the same two temperatures. And if we're using the thermodynamic temperature scale, now we don't even need to know how much heat is added or removed from the reservoirs. All we need to know is the temperature of the reservoir itself, and then we can determine what the theoretical max efficiency would be. And this Carnot efficiency is, again, the highest theoretical max efficiency. And if we increase the temperature of our high temperature reservoir or decrease the temperature of our low temperature reservoir, we're going to have a higher efficiency. Okay, now there's certain constraints. We can't just do this, infinitely. We could increase the high temperature reservoir as much as material constraints will allow. So if we're trying to increase the temperature of our furnace and it's so hot that it melts the material in our boiler, then that won't work for us. Similarly, we're dependent on the types of fuels that we can use and the types of temperature ranges we can obtain using natural gas versus coal-fired power plant versus nuclear. And then we also have to be concerned about thermal pollution and things like that. And then similarly with a low temperature reservoir, in many cases we're using the environment as our reservoir, and there's limitations on that simply because the temperature outside is what it is. We can't artificially reduce that temperature without putting in work, in which case then we're adding more work to our system, which we won't get any additional benefit out of that just by trying to increase the efficiency of our heat engine. Okay, so it's just based on what's available. And then we can use this again to compare our actual heat engines and see how close they compare, rather than looking at 100% as the benchmark. You know, with an electrical system, we can say, okay, I want 100% efficiency on this electrical motor. So I need to use, you know, certain wire materials and resistance and like frictionless brushes and things like that, so that I can try to get 100% efficiency on this electric motor, which is possible. You can have electric motors that are like 99.9999999%, so essentially 100% efficient. And so a lot of times we think that's the benchmark. Well, everything should be 100% efficient, but theoretically, we cannot do that when we're converting heat back to work. So don't look at 100% as the goal. Look at the Carnot efficiency as the goal, and then that makes it a lot more reasonable when we see this is the best that we can do. We're at 55%, but Carnot efficiency is 60. Okay, well, we're close. You know, that's similar to having 95% versus 100. And then again, the thermal efficiency of a reversible heat engine operating between the two reservoirs will always be the same. If your thermal efficiency is less, then you have an irreversible heat engine. If your thermal efficiency is somehow greater than the Carnot efficiency, you have an impossible heat engine. So it can't exist in real life. So let's do an example. This is a Carnot heat engine that receives 500 kilojoules of heat per cycle from a high temperature source at 652 Celsius and rejects heat to a low temperature sink at 30 Celsius. So I want you to work on this on your own, determine the thermal efficiency of the Carnot heat engine, and then the amount of heat that's rejected, so Q sub L, per cycle. So work on that for a minute. Be careful about units, and then we'll come back to it. Okay, so thermal efficiency is 1 minus T sub L over T sub H. T sub L in this case is 30 Celsius plus 273 because we have to convert it to Kelvin. And then we have 652 plus 273 to convert it to Kelvin. So if we calculate that thermal efficiency, we get 0.672. Now, how do we figure out how much heat is rejected to the sink per cycle?
Like how you do it?
Yeah.
Would you like set it equal to the other one, the 1 minus QL or QA?
Yeah, so we could do that. We could say this is equal to 1 minus Q sub L over Q sub H. Or we can just say that T sub L over T sub H is equal to Q sub L over Q sub H. Or we could go the long way around and we could use the thermal efficiency to calculate the network out and then perform an energy balance to find Q sub L. So there's a lot of different ways we can approach it. This one is probably the easiest. However, be careful because this only works for a Carnot heat engine. So don't try to use this on an irreversible heat engine. It only works for a reversible heat engine. Okay, so Q sub L is equal to T sub L over T sub H times Q sub H, which is equal to, again, using our conversion to convert to Kelvin, so 30 plus 273, 652 plus 273 multiplied by the 500 is equal to 163.8 kilojoules. So you have 1 minus 0.672 is what this is equal to, so it's 0.328 times 500. Okay, any questions on that? So again, this relationship only works for a reversible heat engine. If you have an actual heat engine, you cannot use this relationship to find your missing value. You have to perform an energy balance or use the thermal efficiency to calculate workout, things like that. Okay, it only works for a reversible heat engine. So make a mental note of that and make a physical note of that for when you get to the exam. Okay, so we've talked about the quality of energy before, and we have to be concerned about it because as a higher temperature reservoir has greater quality of energy than a lower temperature reservoir. So energy is always seeking to go from a high quality state to a low quality state, and this is manifest because of the principle of entropy. So it's always our desire and always in our best interest to keep energy in a higher quality state and try to use it effectively and efficiently when it's in that high quality state so that we don't waste or lose these energy processes. For example, when we are heating up water, we want to somehow insulate the storage container that we put that water in, right? Because if we heat up the water and it just immediately starts cooling down, that's a wasteful use of our resources or our energy. And so similarly, if we have a high temperature reservoir, we want to do whatever we can to maintain it at a high temperature because we get more use out of that energy when it's at a higher temperature than we do when it's at a lower temperature. So the thermal efficiency will continue to decrease as our source temperature decreases, which is not always a good thing. So let's look at two different scenarios. So from a work production perspective, which is more valuable? Thermal energy reservoirs at 675 and 325 K, or thermal energy reservoirs at 625 and 275 K? So if you want to figure out which one is more valuable, how would you approach that, or how would you look at it? What would be a way to compare those two sets of thermal energy reservoirs? Yeah, so let's look at the efficiency, and how would we calculate that? Yeah, so we look at the Carnot efficiency of each of those two individual systems, and we try to figure out, okay, so which one is the most valuable to us? Well, we want to go with the thermal energy reservoirs that are the most efficient. In many cases, it's going to be the one that has the highest temperature, but in this case, our thermal energy reservoir, the sink, the temperature is changing as well. So we can't just simply say, well, 675 is the best because it's the highest temperature. We have to actually calculate the efficiency. Okay, so let's look at those. Have you calculated them? Which one's better? B. You sounded less confident the second time you said it. Is it because I questioned you? Okay. So thermal efficiency is equal to 1 minus TL over TH. So for part A, we have 1 minus 325 over 675. Which gives us 0.5185. And for part B, we have 1 minus 275 over 625, which gives us 0.56. Okay, so B is a more efficient combination of reservoirs. So sometimes we have to play a little bit of a juggling act, where we say, okay, you know, in this particular scenario, I'm able to get the temperature up to 675, so that's really good, but how much energy are we expending in the furnace to try to increase the temperature to 675 versus 625? So if we can somehow find a lower temperature reservoir to reject our heat to, sometimes that's just as good as increasing the temperature of the high temperature reservoir. So it's really the difference between those two reservoirs and how we can calculate the Carnot efficiency that will oftentimes give us the best case scenario, or how we can maximize the efficiency of our design or our system. So it's important to look at. So here's an example of energy degradation in process. So solar energy is very high quality at the source because the temperature of the sun is about 5,773 Kelvin. Okay, it'd be really nice if we could just put use that as the thermal reservoir itself, right? Okay, well, we can't really do that, so we if we're just looking at the heat of the sun, they use oftentimes solar ponds to collect the energy, which are often at about 350 Kelvin, which is still pretty warm, but it's not warm as we would like it to be compared to the actual temperature of the sun. So they have pretty low efficiencies, because the 350 Kelvin is not that much higher than the ambient surrounding temperatures, and calculating the efficiency with that, it's around 5 to 10%. So this energy from the sunlight, very high quality at the source, is degraded as it travels through space. So if we can find some way to concentrate that energy rather than simply using solar ponds, then we can increase the efficiency of the sun at the source. And the sun is nice because it's essentially a free energy source, right? It's just shining its rays upon the earth, but it's also a temperamental energy source. And so we have to be smart about how we use it, because in certain parts of the country it's not very sunny. Like in Portland, Oregon, they have, I think it's like under 100 days of sun per year, something like that, kind of gray and depressing. Whereas in Arizona, it's like 350 days of sun a year. So we have to be smart about it. There are places in Europe that are quite prolific at using the sun to its advantage. And we often think about solar panels as the main method of which we can use to collect the solar energy. But in many cases, they are using instead arrays of mirrors to concentrate the solar energy. So rather than having a field of solar panels which are somewhat temperamental and you have to have it wired into a grid, and if the panels get dusty, then their efficiency decreases significantly. They require a lot more maintenance. They put mirrors in these arrays. And they use these mirrors, which are controlled by servos, to concentrate all of the sunlight from that area onto a single smaller area on these large towers. And inside those towers, they'll have a steam turbine, and so they'll use the energy from the sun from this great wide large area to get a very high temperature turbine evaporation process going. So they turn the water into steam, it runs through turbine and creates electrical energy. Another method that they use is, instead of having water in the tower and using it to power a steam turbine directly, they will have salt, which salt melts at a very high temperature, and it also remains in a melted state. It has a very large thermal storage capacity. So it takes a long time to melt it, but it also takes a long time for it to cool off. So it's a way of storing energy. So they put all this energy into the salt, they melt the salt, and then at night, when the sun is not shining, as that salt is cooling, they can remove some of the heat from that and use that to power their processes. So there's different ways of looking at this, that although the energy is being degraded from the source is free, okay? So this is a very clean, green, easy way, not easy, but smart way to concentrate the power of the sun to use for our purposes for energy production. And this Abengoa Solar, actually, this is in Spain, I believe, but they have just fields and fields of these that they've created. And there are a lot of countries in Europe that are almost predominantly powered by alternative energy sources, because they don't have coal, they don't have fossil fuels available to them. Everything they get, they have to import. So when we were in Germany last summer, it's like every single house practically has a solar panel on its roof, and it's because they've just made that the priority, that they want to be energy independent. They don't want to have to rely on importing fuel supplies from other countries, because we know those lines can be cut off at any point. So they've really invested heavily in alternative energy sources in Europe.
Doesn't that cost like 20 times what it does for us for coal?
Oh yeah, like they get it from the Middle East too. But yeah, like to fill up a tank of gas, if you do the conversion, it's like $6 to $8 a gallon, depending on which country you're in, like to fill up your gas tank. So, but all the cars in Europe are small, energy efficient vehicles, and many of them run on diesel, which is cheaper because there's less refining that goes into it. Okay, so also a lot of people ride bikes and they walk. So, you know, when energy is really expensive, you make sacrifices or changes in your life, right? So they've been forced to do that because their energy costs are so high. But I don't think it necessarily, there's I think an improvement, if anything, in their quality of life, because the people are a lot healthier. They walk more, they get outside more, they are much more conscious of how they're using energy, and so they're a lot more conservative with it. Like my brother's married to a French woman, And it's like if you walk out of a room and don't turn out the light, it's like you might as well have murdered somebody. They are just so careful, and it's funny because, anyway, yeah, so my brother has funny stories. But it's, you know, we have the luxury in this country of cheap energy sources, right? So we leave the lights on all the time. We have the TV going in every room. We turn the thermostat up to 75 because we can, because it hasn't become so expensive yet that we don't do it. Okay, so, you know, what's it going to take to change that? I don't know. So once the temperature of the heat source is reduced, then the energy is degraded, and it can't be recovered 100%. So even though we can use these solar collectors to collect this incident sunlight, we're still not getting all of the energy that we would have got if we just got it directly from the sun. So if we have energy that's at 1,000 Kelvin and it's cooling to 300 Kelvin, there's really no practical value in that to us. But if we use a heat engine and put it in between these two thermal reservoirs, then theoretically we have 70% of that energy is usable. So high temperature energy in small amounts can often be very useful to us, much more so than low temperature energy in unlimited supply, like the sun shining all around every day, that it's not useful to us unless we do something to collect it somehow. That's the goal. Carnot refrigerators operate on the reverse Carnot cycle, so rather than a network output, we have a network input. And the desired outcome, again, is to remove heat from the refrigerated space. So the analysis is the same as it would be for the irreversible refrigerator or the standard refrigerator, but we have some additional tools for analysis that give us, again, this best possible scenario where we can just look at the temperature of the reservoirs. So we can rewrite the coefficient of performance using temperature rather than Q sub H and Q sub L. And you'll notice that work is left out of the equation because it doesn't factor in if we're looking at the temperature of the reservoirs. We simply need to know those temperatures. And again, if our COP for a reversible heat engine is, it has to be the same as our COP for this Carnot cycle. And then if we somehow manage to calculate a COP that's greater than the reversible case, then our refrigerator can't exist. It's an impossible refrigerator. So as the temperature T sub L decreases, the efficiency of this refrigerator will also decrease, or the performance of this refrigerator, I guess, is a better word to use rather than efficiency. Meaning that the refrigerator has to work harder to maintain that cold space, and the more work that is required to go into the system to try to remove heat, the less effective or the worse performance you can expect. So the same goes for like your house. If you're air conditioning your house to a very low temperature, your coefficient of performance will be decreasing. And as the temperature increases outside, also your coefficient of performance will decrease. So the best case scenario with a refrigeration system is that the temperature outside and inside are approximately the same, because then your system doesn't have to do any work at all to maintain temperature. So let's do an example with this refrigerator. So there's an inventor who claims he has a refrigerator that cools food to 35 Fahrenheit in a room at 75 Fahrenheit. And he says the COP of this fridge is 13.5. So we have to find out if this claim is reasonable. And how would we approach this or do this? Oh. Okay, so we need to calculate the theoretical COP. I don't know what they use to clean these boards, but I don't like it. It doesn't erase anymore. Okay, so we need to calculate the COP of a reversible refrigerator and see if his calculated COP or his proposed COP is higher or lower or equal. If it's higher or equal, then we know it's probably not going to happen. Okay. So COP max, which is the reversible case, is just simply based on the temperature of the reservoir. So 1 over TH over TL minus 1. So in this case, Rankine, the conversion factor is plus 460 to convert to Rankine. So we have 75 plus 460 over 35 plus 460 minus 1. So that gives us a coefficient of performance of 12.4. So is his claim true? No. His claim is not true, that it's not theoretically possible to have a refrigerator with that COP if it's operating between those two temperatures. Okay, so whatever his system he thinks he's designing, it's not real. It can't exist in real life. Okay, because you can never have a COP greater than that of a reversible refrigerator or a Carnot refrigerator. So we can write that one off. Similarly, Carnot heat pumps operate on the reverse cycle, but this time instead of removing heat from a cold space, we're adding heat to a warm space. And the Carnot efficiencies, again, can be rewritten in terms of the temperatures. So in this case, instead of TH over TL minus 1 in the denominator, it's 1 minus TL over TH. And we can compare that to reversible heat pumps to see if we are violating the rules. And then again, as T sub L decreases, the efficiency of the heat pump also decreases, or the effectiveness of the heat pump, because it's more difficult to pump heat from cold outside air. So on days when it's 5 degrees outside, your heat pump is either probably running constantly or it has switched into emergency heat mode. So let's do an example with that. We have a heat pump heating a house during the winter. The house is to be maintained at 21 Celsius at all times. The house is estimated to be losing heat at a rate of 135,000 kilojoules per hour when the outside temperature drops to negative 5 Celsius. So determine the minimum power requirement to drive this heat pump. So we know T sub H and T sub L. So T sub H is the temperature of the house, and T sub L is the temperature of the cold outside air. And then we're told that the house is losing heat at a rate of 135,000 kilojoules per hour. So that's how much heat our heat pump needs to add to the house in order to maintain the temperature at 21 Celsius. So as we look at this problem, those are the parameters. What are some keywords in this problem that tell us what type of analysis we can use? Okay, it's a heat pump, so we know we have to use the right equations for a heat pump. Okay, so constant 21 degrees. That just is, it's telling us the thermal reservoir temperature. But in that very last sentence, determine the minimum power requirement. So what case is going to give us the minimum power requirement? The max efficiency or the reversible system, right? So if we want to know the least amount of power we have to put into this system, we can look at the theoretical perfect system, right, or the reversible system, which again is not going to have 100% efficiency. It's going to have a coefficient of performance of some other value. So we want to look at the minimum power requirement. So anytime you see keywords in problems like that, if you're looking for the max power or the minimum power or the, whatever it might be, best case scenario is always the reversible case. So we have to calculate that. So the thermal efficiency, the coefficient of performance for a heat pump that is reversible, again, is just based on the temperatures of the reservoir. So 1 over 1 minus T sub L over T sub H, which in this case is equal to 1 over 1 minus, and then we have to be careful about signs because it's negative 5 plus 273 to get Kelvin, and 21 plus 273 to get Kelvin, convert 21 Celsius to Kelvin. So we calculate our coefficient of performance to be 11.3. So this is telling us, okay, best case scenario, this will be our coefficient of performance. We want to know the minimum power requirement. So now we need to perform an energy balance on the system or use our equation for coefficient of performance in an alternate way. Because coefficient of performance is also equal to the desired outcome over the required input. Forgot how to write a Q. So what's our desired outcome in this case? Q dot H, right? So we're adding heat to the house. That's our desired outcome, is Q dot H over this network in. So we want to solve for this work net in is equal to Q dot H over this coefficient of performance for a heat pump. In the reversible case, will give us our work net in minimum. Okay, so Q dot H is 135,000 kilojoules per hour, and our coefficient of performance is 11.3. So we can convert this from kilojoules per hour to kilojoules per second, which will give us kilowatts. So there's 3,600 seconds in an hour. So we need to multiply by 1 over 3,600 seconds, 1 hour. And we get 3.32 kilowatts. So that's the minimum amount of energy that we have to put into this system, or the rate of energy that we have to put into this system in order to achieve these goals based on the outside condition, the temperature that we wish to maintain our house. So this is the minimum that we will have to put in. In reality, we'll probably have to put in more than that because our system is not reversible. It's not 100% effective like a Carnot heat pump would be. Now, how would this problem change if we said, okay, now instead of being -5 outside, the temperature is 15 degrees Celsius? What would happen to our coefficient of performance? So if this number is bigger, then this number is smaller, so this number is bigger. Yeah, so our coefficient of performance will actually increase for a heat pump when our temperature outside increases, or as our temperature inside decreases. So for a heat pump, decreasing the range, heat pumps and refrigerators decreasing the range of the temperature difference between the thermal reservoirs increases our coefficient of performance. Whereas the opposite is true for a heat engine, that we get less usable energy out of it when the temperatures are closer together. But for this, we have to put in less work, and it's generally more effective. We have higher performance when it's not quite a drastic temperature difference that we're trying to overcome with our heat pump or with our refrigerator. So like if you keep your house at 90 degrees and you're trying to maintain your fridge at whatever temperature, that's going to be more difficult. So we can look at the coefficient of performance with temperature. So if we're cooling and we are working between these temperature limits, that our coefficient of performance will increase quite a bit for a cooling system if we're not trying to overcome a huge temperature difference between our house and the outside. And then the same goes for heating system. And you notice that the reversible case for a refrigerator, it's easier to get a higher coefficient of performance for that refrigerator in those cases. Well, maybe not. Okay, so you can kind of see what I'm talking about, that you've probably experienced this in practice. It's harder to keep your house warm when it's colder outside, right? Your heat pump has to work harder. And it's because, in part, the coefficient of performance decreases the larger the temperature difference is between what you're trying to heat and where you're getting your heat from. Okay, let's do another example with a refrigerator or an air conditioner system. So we have R134A as the working fluid, and it's used to keep a room at 26 Celsius by rejecting the waste heat to the outside at 34 Celsius. The room gains heat through the walls and windows at a rate of 250 kilojoules per minute, while the heat generated by the computer, TV, lights amounts to 900 watts. So we have heat coming in just from the outside, as well as some heat being generated inside our house due to appliances. The refrigerant enters the compressor at 500 kilopascals as a saturated vapor at a rate of 100 liters per minute and leaves at 1200 kilopascals and 50 Celsius. So we want to determine first the actual COP, the max COP, and then the minimum volume flow rate of the refrigerant at the compressor inlet for the same inlet and exit conditions. Okay, so there's a lot in there. We know that this is a refrigeration system, but we also know that we have to analyze and perform an energy balance on the compressor in order to figure out some of the other inputs to our system. So if we want to find the work in, we're going to have to look at the compressor and see what the inlet and outlet conditions are. So there's multiple steps to this problem, but we're combining some of the concepts and terms from Chapter 5 with Chapter 6. Okay, so we should be able to do it because we've learned all this stuff. Okay, so 6-108. -110. Gotta change the slide. Okay, so first thing we should do is perform an energy balance on the compressor, and we'll find, so Q dot in minus Q dot out plus work dot in minus work dot out is equal to M dot times H2 minus H1. So for a compressor, we don't have work out, we don't have any heat losses, we're assuming. So this work dot in is equal to M dot times H2 minus H1. Okay, do we know M dot? What do we know? Okay, we know the volumetric flow rate. How would we convert a volumetric flow rate to a mass flow rate? Yeah, so V dot is equal to M dot times specific volume. So we're going to need to know the specific volume at the inlet in order to calculate M dot. We can do that. Do we know H2 and H1? Yeah, we can find them pretty easily from the tables. So state of the fluid at the inlet is a saturated vapor at 500 kilopascals. So we just have to look at our table at 500 kilopascals and use V sub G at 500 kilopascals. So we can look those up. So state 1, V sub G is equal to 0.04118 meters cubed per kilogram. And then H sub G is 259.30 kilojoules per kilogram. Then we can go to state 2, which is going to be a superheated vapor, I believe. 1200 kilopascals, 50 Celsius. It's table A13, whatever that is. So we find H2 is equal to 278.27 kilojoules per kilogram. So we now know H2 and H1. We can calculate M dot is equal to V dot over V1. So that's 100 liters per minute. We convert that to seconds, 1 minute over 60 seconds, and then convert liters to meters cubed. So 1 meter cubed is equal to 1,000 liters divided by V1, which is this 0.04118 meters cubed per kilogram. So we find M dot is equal to 0.0405 kilograms per second. So then we can plug in all the numbers using M dot, H2, and H1 to find our work dot in is equal to 0.0405 kilograms per second multiplied by H2, which is 278.27 minus 259.30 kilojoules per kilogram. So the work dot in is 0.769 kilowatts. Okay, so we found that, but we still haven't figured out anything that we need. So we haven't found the coefficient of performance for the refrigerator for the actual case or the reversible case, and the minimum compressor volumetric inlet. Okay, so we need to take this work dot in now and our Q dot L and calculate a coefficient of performance using that. So Q dot L is a combination of the heat that's entering the room from the outside, as well as the heat generated by the appliances. So that's the amount of heat that has to be removed by this air conditioning system in order to maintain the room at 26 Celsius. So we have Q dot L is equal to 900 watts plus 250 kilojoules per minute. And can we just add these two together? No. So we have to convert kilojoules per minute. 1 minute is 60 seconds, and 1,000 joules per kilojoule, so that we can add those together. So we end up getting 5.07 kilowatts. I guess I converted this one to kilowatts instead of vice versa, but you get the picture. So it's either 5.07 kilowatts. So now we can calculate our coefficient of performance because we have our power input is 0.769 kilowatts, and our Q dot L is 5.07 kilowatts. So our coefficient of performance actual for this refrigerator is equal to, what is our desired outcome? Our desired outcome for a refrigerator is QL, right? Because we're trying to remove heat from the cold space to make it colder. So it's Q dot L over work dot in. So we calculate our actual coefficient of performance is equal to 5.07 kilowatts divided by 0.769 kilowatts. So we get our coefficient of performance is equal to 6.59. Okay, so that's the actual coefficient of performance. We can then calculate our theoretical coefficient of performance, and it should be higher or lower? Higher, right? Because it should be better. So 1 over TH over TL minus 1 is equal to 1 over T sub H, which is 34 degrees plus 273, and T sub L, which is 26 degrees plus 273 to convert to Kelvin. So we calculate a coefficient of performance of 37.37. So quite a bit higher than what we're actually getting. And that's not unusual. So the best case scenario is with this coefficient of performance. So this last part, calculating this minimum compressor input. Okay, so we can then go sort of backwards and calculate now, instead of using this volumetric flow rate that we already have to calculate the work input, we can use the coefficient of performance to calculate a theoretical minimum work input and then figure out what the volumetric flow rate would be with that theoretical minimum work input. Okay, so the inlet and the outlet conditions of the compressor don't change, so we're not changing the temperature of the fluid that's running through there, we're not changing the pressure. All we're saying is, how much slower could we put that fluid through if we didn't require as much work? Okay, so work dot in for the best case scenario, if COP for the reversible case is equal to Q dot L over work dot reversible in, then we can calculate the reversible work is equal to Q dot L over the coefficient of performance for a reversible heat engine. So Q dot L doesn't change. All that's changing is this work input. So Q dot L is still 5.07 kilowatts, but now we're saying that the coefficient of performance, if it were 37.37, then we calculate our work minimum to be 0.136 kilowatts. So instead of the 7.769 kilowatts, we're saying, okay, now we only have to put in, if this were a reversible heat engine, we'd only have to put in 0.136 kilowatts. And in order to do that, we would need to have our fluid flowing into the compressor at a certain volumetric flow rate. So then we go back to this equation and we calculate the mass flow rate if it were reversible work instead. So the mass flow rate is going to be, for the reversible case, the work reversible divided by H2 minus H1. So remember, again, these inlet and outlet conditions aren't changing. It's still same temperature, same pressure. We're just saying, okay, we want to figure out what mass flow rate we would need if it were reversible. So the reversible work is 0.136 kilowatts divided by this H2 minus H1, which is 278.27 minus 259.3 is equal to, that's kilojoules per kilogram, 0.0072 kilograms per second. So we found the mass flow rate. Now again, we have to convert it to volumetric flow rate. So V dot reversible is equal to specific volume at state 1 times M dot reversible. Excuse me. So the specific volume, again, doesn't change. 0.04118 meters cubed per kilogram multiplied by this M dot reversible, so 0.0072 kilograms per second. And then if we convert that to liters per minute to compare, we have to multiply by 1,000 liters per meter cubed and 60 seconds per minute. Then we get 17.76 liters per minute. So instead of needing to have the fluid flowing through at 1,000 liters per minute, 17.76 liters per minute, if it were a reversible refrigerator with the same ambient conditions that it was trying to meet. Okay. So you can kind of see how these analyses go. Sometimes we get confronted with a big problem with lots of different words in it. We get confused, but if we start, draw a picture, think about it fundamentally. What is it that I'm actually trying to figure out? Okay, this is a real refrigerator. These are the conditions. What if it were a reversible refrigerator? How would that improve my work input? Okay, how would that change my my Q sub H possibly, depending on what the criteria were. Okay. Household refrigerators, you can see the evolution of the refrigerator, sort of. Turn that off. That back in the olden days before electricity, they used to just dig like big storage places inside of a hill. That's what they used to keep things cool, so like a root cellar. In places where there were cold winter climate, they would actually go to lakes and cut blocks of ice and then store them in here in straw and earth to try to maintain things at a very cold temperature. That's how they did cold storage in the olden days. So you can imagine they wouldn't have a fridge full of perishable foods. They would have to ferment things or can them or dry them, but they couldn't just keep a lot of fresh food around. Then as people developed communities and suburbs, they needed to find some sort of a way to keep things cool at their own house if they didn't have a root cellar. So they would use these ice boxes, which my grandmother still refers to the refrigerator as an ice box, because they would have this insulated box and there would be an iceman who would come maybe once or twice a week and deliver ice to their house, they would put it in the ice box, and that's how they would keep things cold. Ice boxes improved by becoming a little bit more furniture-like rather than an outside appendage, that they were these insulated boxes which were nicer but still didn't have electricity. They still needed ice to keep them cool. And then as we gained electricity and indoor plumbing and all the other niceties of life, and refrigerators have continued to improve to the state where they are today. And actually over like the last maybe 10 years, they haven't done much to improve the conditions or the quality of refrigerator. If anything, they've gotten worse because they're less dependable and reliable. They've input more electronic aspects to it. So, you know, they have these really cool ice makers and drink dispensers, and you can have it, you know, dispense hot water or cold water or ice that's been chipped or, I don't know, whatever. But then there's more things that tend to break, and then your refrigerator is useless because the computer board has gone out, not because the compressor's not working. So the evolution of refrigerators, it's kind of nice. About the average refrigerator costs about $72 a year to operate, so they're not very expensive to operate from an electric standpoint. And that's about half of what it was for refrigerators from 25 years ago. So if we look at this old style, like they have in the engineering lab, those are more expensive to operate than the newer high efficiency, particularly the ones that have the freezer on the bottom versus a side-by-side. These are more energy efficient because there's not a wall in between, a vertical wall in between, trying to keep the cold cold and the cold less cold. Having it separated vertically rather than horizontally rather than vertically, actually you're able to maintain the heat easier because heat tends to rise, and so cold stuff tends to settle to the bottom. Anyway, rather than trying to do it side by side. You know what I'm saying. Yeah, above your freezer. Yeah, that's actually more energy efficient, usually, assuming that they've done the design properly. And they're designed to have a low energy cost, low purchase cost, and then max food storage. So they've tried to make the interior bigger. And replacing a really old refrigerator can mean a huge energy savings in your home, which is about a ton of CO2 a year. So if you have a 25-year-old refrigerator that still works, it doesn't mean you should go out immediately and replace it with a newer, higher energy model. But when you are shopping for a refrigerator, if it costs a little bit more to buy one that's more energy efficient, it's probably going to save you money in the long run and be better for the environment. However, don't try to get the one with all the electronic bells and whistles because they tend to break. And they will replace every single part on your refrigerator before they will replace your refrigerator. Like if you have to have a repairman come out on warranty, they don't just give you a new fridge, they replace every single part on there before they'll actually give you a fresh new fridge. So fortunately, ours, several friends, ours, knock on wood, has not had any problems. It's the fridge that came with our house, and actually it's been fine. But yeah, like I have friends that have bought new dishwashers, new refrigerators, and it's like they're these really cool, great appliances that do amazing things, but then a computer board goes out and it doesn't work at all, you know? So it's like, is that better? I don't know. Sometimes it's not. It's more frustrating. And yeah, so that's what the companies do. They don't want to take your old broken refrigerator to their place. They want to fix it in your house, and they'll just send a repair person out. So some things that you can do to make your fridge more energy efficient is open the door less. That one should be obvious. And then cool hot foods to room temperature before you put them in the fridge. So if you've got a pot boiling of soup and you just immediately put it from the stove into your refrigerator, that's going to be much more energy taxing, and it will cause foods around it to warm up and potentially spoil. Cleaning the condenser coils, which probably no one ever does. In most cases, they're under the fridge. Sometimes on older fridges, they're on the back. But as those condenser coils get dusty and dirty, they can't shed heat as easily. So it's like you're insulating your condenser coil, which the purpose of the condenser coil is to remove heat from the refrigerant and put it back into the room. But if it's like insulated by dust bunnies, then it can't do that as well. Checking the door gasket for leaks, so you can put a dollar bill in, shut the door. If you can easily pull the dollar bill out, then you may need a new gasket around your fridge. Avoid unnecessarily low temperature settings. And then sometimes they have like a power saver switch where you can tell the refrigerator to use cool air from the freezer to keep the refrigerator cool before it kicks on the compressor, which sometimes helps. And then don't block the airflow. So don't stack all of your cereal boxes on top of the fridge. There needs to be airflow around it so that the heat can be exchanged with the air in your home. That's how it works. Okay, so energy selfies, this is mine. I look pretty good in that picture. No, this is because I took this picture a long time ago and I didn't think about, and I don't like taking selfies anyway. But this is just an example of some things that I've seen on vacation. This was in January, not on spring break, but at Legoland, Florida. All of their handicapped parking structures, the roof of them is actually just these solar panels, which there's not even a roof which the panels are on top of. The panels themselves are the roof, which is kind of cool. You can see from this perspective. And so they have all the conduits and the wiring and the transformers coming down on these big pillars that hold up the roof. And then they send it into their local grid. So they use whatever incident sunlight to transform using these solar panels into electricity, and then they use it in places in their park. So there's a building in the park that has, it's like where the invention, I can't remember what they call it, but it's like this place where kids can go and they can do experiments and make stuff out of Legos and stuff like that. And so this building is completely powered by the solar panels from the parking lot, and then I think they also use the energy in some of the other places too because they have excess. But this was just like a view of the amount of energy that they were creating on particular days. So you can see how it peaks between 8 a.m. and 4 p.m. And this was in January, so it's a lot cooler, and the sun is at a lower angle in January. So in the middle of the summer, these peaks would be certainly a lot higher. But you can see how it peaks during the day, and then of course it's flat at night because there's no sun. But it was kind of interesting to see, and there are more companies that are investing in alternate energy, both from a cost-saving standpoint, but also just out of environmental stewardship. That if they're able to power even one building at their park with solar panels rather than using fossil fuels, then they can save 56 tons of CO2 at that particular point. And these I think were. It wasn't clear to me if it's from the beginning of when they started this. So they started this program in January 2014. So if it's 56 tons since January 2014, which would have been 3 years, or if it was like a year-to-date kind of thing. I don't know. They didn't have a lot of details on that. But it's interesting to see, and it's nice to see it around. It's nice to notice it. So I hope that as those of you who did the extra credit assignment, that you really took the time to kind of look around you and see what people are doing, what companies are doing. So that's it.